This is part 1 of our video for showing our course project. In this video, I'm going to describe the reinforcement learning problem that we solved in our course project. The key is the simulator that we used. Our simulator is based on the so-called finite horizon Bayesian optimization problem. The goal is to find the global minimum of a black box function. Bayesian optimization does this by sequentially evaluating the black box function at different input locations. In this 1D example, the black box function is the black curve here, what I call the true function. We start with 4 data points, and we sequentially evaluate the true function at other input locations to find the global minimum. What the simulator does is that it takes in the current data points, builds a model with them, and uses the model to predict the outcome of the evaluation of the true function at any input location. For example, if we choose to evaluate the true function at this location, we can use the simulator to simulate a data point at this location, like this. And then we can observe a reward for this new data point. Because we are minimizing the true function, the reward we get is the vertical difference between this new data point and the best existing data point, this one. And we can continue to do this for a finite number of steps. And this whole process is what our simulator does. Note that we never evaluate the true function in this simulation process, but we only use it for conceptual purpose. We then plug in this simulator to the DeepQ-Learning engine that we got from class. We run the DeepQ-Learning to optimize the input locations where we choose to evaluate our true function. Of course, there's more details in this whole process, but this is a basic sketch of the reinforcement learning problem that we solved. Let's look at our actual experiment. We experimented on optimizing a 2D function called Brownian function. We started with 10 data points, and we simulate the 10 future evaluations. In each of the future evaluations, we can choose the input location from 6 choices. We plug in the if simulator to the DeepQ-Learning engine, and we fine-tune the hyperparameters of the DeepQ-Learning process and observe the performance of our DeepQ-Learner. This is an example of our actual outcome. In the next video, we are going to show the full result of our training process.
This is the second part of our video. We will show you how to tune the parameters and their corresponding result. Because the training process is quite time-consuming, we only test 8 different sets of initial value, and the parameters we have changed includes the number of episodes, the decay rate, which balance the exploration and exploitation rate, and how many times do we update the reward. Also the memory length and the step length, which is called alpha, and our active function we use ReLU here. And as it shows in the copy 1, we use the 1 as our decay rate, which means we always accept the random reward, and in the result you might not see a clear increasing trend in the average reward, and the total average reward is around 1.05. One of the best setting of our data could be the copy 7. As you might say, in the later episodes, it shows growing behavior or increasing behavior clearly, and even though the average parameter is a little bit below than 1.05, we still accept its better result than the random one. And due to the time limit, we don't have enough time to explore enough data, but during this process, we do benefit a lot from how do we using the Q-learning into the research problem. And thanks a lot for your teaching during the whole quarter. Thank you.